Okay, so this talk is, well, about graph and hypergraph databases and what the heck does that even mean? So I'm going to kind of start from the beginning. And it's all about really how to describe relationship data. And so what do we mean by a relationship? And that's a very good question, which I'm not going to answer. But one model is a network, because you've heard about that for, since Facebook started, which is what, 10 years now, maybe? And so here's the metaphor. That's a network. That's our relationships. That's actually a black widow spider web. And I'll let that metaphor sink in. Okay, so okay, here's a picture. It's an undirected graph. By graph, I mean something that has some nodes or some vertexes, and they're connected pairwise. And this is kind of the motivating metaphor of a whole lot of stuff. And you notice one thing about this network or this graph is that it's undirected. So it's only you friend me, I friend you. And well, okay, that's a model of relationships. Question is it a good model and does it fit our experience? I don't know. Here's another one. That's also an undirected graph, an undirected network. That's the internet backbone. I'm told. Somebody told me on the internet that was the internet backbone. And I believe it. And you can see the major hubs and so on and so forth in there. And again, I guess the internet backbone should be two-way. If you're connected and you can talk to each other. Okay, here is a different sort. Maybe you want to blur the camera at this point? Good. So this is a realistic fifth grade girls social network. The arrows means that the tail of the arrow likes the person who's at the tip of the arrow. This was in my daughter's head 2 years after the event. And I randomized the names. They don't reflect any real person at this point. But when I eventually replace this picture, I'll take the statistics from this and make a random version of the same. Okay, here's another one. You can show this one. This one is a piece of the World Wide Web. It's a piece of the World Wide Web surrounding Wikipedia. And you notice that the little arrows there are sharp at one end and broad at the other end. And that refers to a link going from the broad end to directed at the target at the sharp end. And that's just a very, very, very small piece of the internet. Okay? And there is the attribution. So web pages are nodes in this network, and directed links are directed edges are specified by hyperlink in the one web page pointing at the other web page. So the actual edge, the actual directed edge, the actual arrow has some data attached to it that tells you where to go, and it might have some other data as well. And it's going to look like that. Okay. So what does data describing a network look like? It looks really boring and stupid, but okay, here it is. I made a random undirected graph. And so I made 10 nodes, just V0 through V9, vertex 0 through vertex 9. And I printed them out right down there. You can see that those are the 10 things. And I made the all possible edges. Well, because it was undirected, it doesn't matter whether the bigger number or smaller is, really what I want is a set. and okay, that's kind of what I got there. And so to make a graph, well, I'm just going to choose, I could take the complete graph, which would have an edge connecting every two vertex, every two nodes. But I chose a random subset of that. And you're wondering, how is that a graph? And each of those edges specifies a link between those two vertices, between V0 and V8 there, between V5 and V4, and so on and so forth. And, oops, that's because I restarted. That's what the graph looks like. And each one of those little circles is one of the is one of those vertexes V0 through V9, and each line is specified by one of those pairs of nodes. Okay, and if you chose a much bigger vertex set and a much bigger edge set between them, it would start looking a lot more complicated. So what about a directed graph? How would we do that? Well, we take the same set of nodes and we take possible edges, or all possible sources for an arrow and all possible targets for an arrow. And I take a random subset of those, and well, it's modeling that as a ordered tuple now. Okay, so it has an order to it. It's not a set, and it would look pretty much just like that did, but you'd have some directions to those edges, so you can put little arrows on them. And what we do with graph databases is an hypergraph database is a lot like that, only more complicated. You just have much bigger sets of nodes and much bigger sets of edges. And you can attach much more information to the nodes and to the edges. Yeah?
What package are you using to print these graphs?
I gotta make a shamefaced confession. I went to Mathematica to do this because I wasn't sure what Python, is there one?
I think so. I don't know. It's not as nice as Mathematica.
Okay.
There's one called NetworkX.
Yeah.
What is it?
NetworkX.
Network X? Actually, I knew that, but I forgot it. But thank you. Okay. So what do I want to compute with a graph or a network like this? And when I say compute, well, the internet has, I don't know, a couple billion web pages now, and each of them has maybe 10 to 100 links. So there's maybe a couple billion web pages and a couple 100 billion links. When we talk about computing with a network, in some of the most interesting cases, that's a heck of a big computing job. So what do we want to compute with data that big is PageRank. Have you guys heard of PageRank? That's what Google supposedly uses, or at least started using 15 years ago, 20 years ago, when it first started out, to rank the listings it gives you on the page by the most important to less and less important as you go down the page. And well, some other things we might want to do is we might want to find organizations. We might find groups in that graph of connection. And there's some people over at Lincoln Lab and Sandia Labs that think about that stuff a lot. We might want to break the graph up into pieces, like for marketing segmentation, for market segmentation. So you might want to break it into pieces where people in one or whatever in one partition of the graph has a more or less homogeneous preference for pretzels or whatever. Okay, so how does PageRank go? And the idea is you start basically with some random weights. Each web page has a random weight or a constant rate, constant rank. They're all ranked the same. And for a web page I that's the targets of hyperlinks, ij1, ij2, all through ijn, for those web pages j1 through jn. And so you notice I've put a pair of indexes there for these hyperlinks that I'm asking you to imagine. That just tell me what web page I'm going from, the J1 through the JN, and what web page I'm going to, web page I. And suppose that the web pages J1 through JN have some current weights, WJ1 through WJN. And each web page J has N sub J outgoing links. So when I have a link to one given web page, I have a certain weight, and I'm going to allocate 1 over N sub J of my goodness to the next guy down the line. Okay, so the update rule is this. I have some damping factor D, and Wi and one step is going to be the old Wi times a factor less than 1. So D is going to be between 0 and 1, and 0.85 is a good number. And then plus D times the average, or D times the sum of the weights from all those other guys. So here's the smiley face picture of that. This big guy has the biggest weight, and it gathers weight from all of these guys that point at it. Okay, now imagine doing this for 1 billion different web pages or 2 billion different web pages. And that's my attribution to the smiley face link. Okay, so here's a theorem. I'm a mathematician too, by the way, so I get to use that word. This iteration actually converges to a limit. Okay, and you could actually find the actual limit using some algebraic eigenvector methods, and it would cost you like n cubed, where n is 2 billion. So it's not very feasible, to say the least. Does not scale to the size of the internet, and or you could do this. You could locally step through this. You could run through all the nodes. Okay, all the web pages, and okay, you look at who's pointing at it, and you say, okay, I'm going to take this much weight from each of those guys to make my new weight. And how the heck would you do that when you don't even have all of your web pages in one server? So what you have to do is you kind of have to walk through the internet graph, and as you go along, take some weight from its neighbors, from its upstream neighbors, and then eventually, when you've done that once, you got to do it again. And when the internet was 200 million nodes, it took about 56 iterations to converge. So it's going to take more than that now. But you can do that job in a distributed way on each little server that has a tiny chunk of the index of the internet. But and it converges. Should converge. Does converge, I hope. So point is this works by a process called graph traversal. And graph traversal is you visit, check, compute at each node in this graph. So you can walk around the graph from web page to web page and do this computation at that particular web page. So how do you do this efficiently is the question. How do you implement this? And well, one way to do this is with some graph databases. Neo4j is a popular one. It's not cheap. ArongoDB, I'm not sure about its status. OrientDB is open source at least. When I tried it, I found it slow, painfully slow. I hear that they were trying to improve, and they may have. And there's some interesting, you know how, does anybody, for those of you who have any brothers and sisters, when you were a little kid and you were driving in the back of the car where your parents were driving you to the ocean or the mountains or wherever you were going, and you know, he touched me and all this stuff. There's some of that going on between Arango and Orient. If you find, if you search, if you search on the internet a lot.
So Tom, what are you trying to do with these graph databases?
With the graph database, what I would like to do is I'd like to be able to do a walk along the graph in graph traversal.
You're not doing PageRank. So,
You could do PageRank with this.
I mean, specifically, what is motivating you? What sort of application should I be thinking about where the answer is you need a graph database?
Where you want to do graph traversal efficiently, and all of those algorithms, all of those jobs, the graph partition, the finding neighborhoods, can be done with graph traversal. Whether they're done well, I don't know. All of my favorite algorithms are O of n cubed or O of n squared, and they don't work. I would do things otherwise if I could, but you have these approximate algorithms for doing things like this.
I can maybe
Please.
interject a few examples. Like, you might want to use this kind of thing if you had a network you were interested in, like, say, Twitter, and you wanted to figure out who are the influencers in that network. So, like, that is one way that data scientists will use this kind of thing. I don't do that, but maybe you want to figure out if you're doing, like, a recommendation algorithm and you want to say, like, oh, you know, person X should follow person Y. So well, how do you decide that? Well, you probably did something like this to figure out who's already connected. And if person 1 is connected to like 5 of the same people as person 2, then maybe person 1 should follow person 2. That kind of thing. But you'd only know that if you crawled the connections of all the people. I think like sometimes it gets used. I have another example.
We use it for firewall rules quite a bit. So the whole node structure lets you look dimensionally around at each connection that's going through a firewall or a route, so that you can do comparison and contrast that follow things through. Very efficient for that.
Thank you. Those are really helpful.
So I'm using it to well, look at some Bitcoin transactions
That's a network.
and follow them. It's a nice network. It's a special network. Okay. Okay. So here's a different model of how relationships work, and I'll explain to you why the graph network is not good enough. So this is a football team called the Hamilton Flying Wildcats, about 1906, I think, 1909, 1906. Okay. Clearly, they were all in relationship to each other. Okay, but no single pair of them might be in the kind of relationship where they say, "Hey, buddy, let's go drink a beer and talk about, I don't know, whatever Canadian politics was in 1906." Okay? So there are these multi-way relationships that are important. Okay? And they may be taking place while there are also pairwise relationships, or there may be no pairwise relationships at all. Okay? So we can think of the football team as a hyperedge. It's not an edge that is between two individuals. It's an edge that's between all of those people on the team. Okay? And that sort of structure, when you have edges that have more than a pair of things in them, is called a hypergraph. It is not in hyperspace. It is like a graph on steroids. And in some ways, the properties, because you have more kinds of edges, the properties of hypergraphs are harder to come by. But they're also useful for a more incisive model of certain kinds of things. So let's see. That's a simple picture. Yeah.
With this hypergraph edge, is there the same kind of thing where it's directed and undirected, or is it just?
Yeah, you can do that.
Okay.
You.
What do you mean that the data is harder to come by?
I didn't say the data was harder to come by. The understanding the structures are harder to come by, and understanding of the structure. Because that simplicity, you only have to deal with pairwise edges, well, is a useful simplification. It makes things more transparent. It constrains more what could happen. So there is a example, thanks to Wikipedia, of a hypergraph. We have some vertexes v1, v2, v3. We're v4, v5, v6, v7. And there is a three-element hyperlink that contains v1, v2, v3 up above there. And two of those vertexes, v2 and v3, are also in a pairwise actual edge, not a hyperedge. But v3, v5, and v6 are in a hyperedge. v4 is all by itself. It's just connected to itself. And v7 isn't connected to anything. Yeah.
What's the difference between V4 and V7?
V7 doesn't have. Well, in the sense that so V4 talks only to himself. Since you work with developers, you know this kind of person. Okay, V7 doesn't talk to anybody, not even himself.
So it's a self-referential edge. Is that what you're saying?
That's a self-referential edge.
If we thought long enough, we'd probably think of an example.
Yeah.
Well, I was thinking like in Twitter, like V4 would be someone who just talks and like nobody pays attention to what they're saying or no one likes them. They were just like.
Well, I'm on Twitter and I don't ever talk.
Okay.
I listen a lot.
V7 would be like having an account but never saying anything.
Yeah. Well, I said something a couple of years ago, 3 years ago, 4 years ago. It was liberating, but I enjoy my chains. Okay, so so we had this image before that was a good metaphor for us, a geometric metaphor, which is for graphs, which is edges connected by lines. Okay, and why does that make sense? Well, 2 points are in a line as long as they're not the same point. Okay, if we have 3 points in an edge, well, 3 points determine a plane if they're not in the same. So we can say that, okay, here's a metaphor for a hypergraph. We have that little triangle in there. That is 3 points that are in that little green triangle up on top. That is 3 points that are connected by a three-element hyperedge. And that blue thing, it looks like a pyramid. It's actually supposed to be a tetrahedron. But so that's 4 things. That's in a 4-element hyperedge. And then you have some normal edges. You have different kinds of edges.
But you've represented this here as a graph.
It's not a graph because I have three things connected together. My tetrahedron is a solid object, in the sense that four distinct points in space determine a three-dimensional figure, a solid three-dimensional figure. So there is a skeleton to it, which is a graph. But actually, you fill in the edges and everything in between. Sarah, did you have a question?
I guess my question was sort of that, is there a better library for plotting these things?
I did that with Mathematica a long time ago. But I'm thinking that some of the game engines would be useful for doing this kind of stuff.
Yeah, I know like Matplotlib does 3D graphs pretty well, but I don't know if it can handle something at like a large scale.
So I need something that has three-dimensional graphical primitives. And I think, I'm not sure if those are around. So here are some hypergraph databases. The ones I could find are hypergraphdb.org. I know nothing about it. The other one that I'm actually using is the Vertex project Synapse HypergraphDB. And I will show you how to do that. Okay, so there's a nice, I suppose that Synapse is a Python wrapper on some C code or some C++ code or something like that. So all I'm going to use here is Synapse, the Synapse module, and a couple of other things that help me deal with the operating system. So okay, I said lots of words. I better go through them. Synapse is a hypergraph database, open source project, is currently under rapid development. The people that are developing it are experienced programmers doing lots of smart stuff. And much of it I don't understand what they're doing. Okay? I sweated blood and tears to figure out the stuff I'm going to show you. Because there are some rather extensive docs, but they were written for people that are equally smart and equally experienced. So my descriptions are going to be incomplete, and my code, I can promise you, is clunky, and so do your own diligence. They do have a Slack channel, which you're welcome to join, and they sometimes they're actually quite helpful.
I should have given that same disclaimer for all of the 30 presentations that I've given.
Okay. So nodes in Synapse come in two flavors. So you would like each node to have a uniquely identifiable primary property. Okay? When you ingest a node or add a node like that to your database, it is deconflicted against all the other nodes you already have. Okay? Which is a nice thing, because you don't wind up with lots of garbage. On the other hand, there are nodes without a uniquely identifiable property, like it could be John Smith or Tom Taylor. Okay? And there are a lot of people with my name. So when you add a node like that, it will be assigned a hash of some kind, some uniquely identifiable, some unique identifier. And it's your job to make sure that all the other John Smiths or Tom Taylors in there are not the same. So you have to keep that in mind. The Synapse module comes with a large number of forms prepackaged. And the guys that are building Synapse are pretty much interested in internet security. And a lot of their forms are related to that. So.
Wait, what's a form?
Oh, I will show you what one is.
Great.
Each individual form comes with a number of properties prepackaged. And they are so good that they made it that when you add a node corresponding to one of their already prepackaged forms, it will take that data that you give it and rip it apart a little bit to populate some of the secondary properties. And we'll see that. So cyber threat analysis is particularly well developed in this. So their name for one of their databases is called a cortex. And they're doing a metaphor with a brain where you have brain, neurons connected via synapses to other neurons and so on and so forth. So each cortex comes with a number of, more traditional databases behind it. And they have a RAM database that's really fast and it dies as soon as you shut off your machine. They have these lightning map databases, so it's a B-tree database, LMDB, SQLite and Postgres, and maybe some other ones. I will say that they're popping out updates about once a week, and so from what I was just seeing, the databases, these 4 databases are the ones that I found when I first started looking at it. It looks like they've got some new ones, although they're wondering if they should drop Postgres. Okay, you can also invent your own forms and properties, but you have to tell your cortex what they are, or it won't know, because it has the useful property that if you try and feed it some garbage, it's just not going to put it in. Okay, so it has to know what the forms and properties are when you tell it to ingest a node with that particular form and property. Okay, so did I lose my terminal?
I think it's over there on the right.
There it is. Okay, so I'm going to. We notice there's nothing in that data and that directory. So now we come back over to here. And I'm going to change into that directory and start up a cortex in that directory. Oh, because I didn't do that. I thought I did, but I didn't. Okay, so now we can go look in there and do an ls minus LAH. And we see there's 2 gigs of database there. That was quick. It's not a real 2 gigs of database because it's a memory map database and it just reserved some pages in there. And it tends to, as you start to shovel stuff into that database, it will increase in size in increments of 1 gigabyte. And that's the specialty of the LMDB. Here is something that took me a very long time to learn. When you want to close that database, you add you do the fini property and we'll close it. Otherwise, you will collect lots of databases and eventually things will start crashing on you and you won't understand why. That's documented nowhere particularly well as far as I can tell, but I found it out on the Slack channel. So let's see what forms we get for free. We're going to get the tuple forms. There are a lot of tuple forms. Tuple is a tuple form. That's because each node is packaged as a tuple in which one is the unique identifier they give you, and the other is a dictionary with all the data you told it to put there. And we'll see some of that.
So are these the keys for them?
No. Well, no.
Okay.
This is one of the dictionary keys.
Okay.
These are some of the dictionary keys. Okay, so we have files, some things about files. We have some geolocation things. We have a lot of INET things and a lot of different properties of INET things. Domain names, URLs, IPv4 and IPv6. Okay. So let us, lots and lots. Is this going to let me go down or what?
Yeah, go off the, yeah.
Okay. So let's check how many nodes we have. So a tupho is what they call a node, tuple form. Okay? And let's see how many we have that have of the form INET URL. And oh look, we have none. That's because we haven't entered any yet. So let's put one in there. So we're going to form a new tuple by this particular, in this particular form with that particular primary property. Okay, and that is the tuple we form. That's the identifier. That's the primary property right there, that web address. And oh, by the way, it pulled out a fully qualified domain name from it to give you a secondary property. It pulled out a port number, 443, for, well, whatever the port number HTML uses. And it tells you when it was created. It tells you that it's new, and so, some other things. Yes, that it uses internally.
How come, so it seems like it knows a lot about URLs.
Yes.
Is this like a particular form that knows about URLs? Or
Yes.
Is it just
I think that's what it means to be a form, is you have some knowledge of.
Yeah, so you tell it you're going to give it a URL, and it knows to find out the piece that's the domain name, and it knows that it comes in an HTML thing, and
so there are other types of nodes that don't know anything about URLs?
yeah,
Okay,
there's that whole list of them up above that I gave you.
okay, so
And you can invent your own.
okay, so the internet URL thing has like all kinds of magic about
Yes.
URL. Okay.
So which, if you're going to be doing with internet stuff, is helpful. You don't have to do that by hand. Okay, so now, nice thing about form the tuple form by property is that it tells you what it formed. So this is helpful because you can, if you're like me and you screw things up repeatedly over and over, it's helpful to see whether you actually got an actual tuple form or just an error message. Okay, so let's go back and check to see if we have any INET :URL forms. And yes, we have that one we just entered. So let's put some more in there. Let's put the football URL in there and the ArangoDB, Wikipedia ArangoDB URL in there. And we're going to use this form tuples by properties. Form tuples by properties. So it's a plural thing. And you can give it any iterable, apparently. You can give it a generator in particular. So you don't have to put what you're going to load into memory all at once. So we'll do that. And I'll put those two new things in there. So how many do we have now? So we're going to get them by that property again. And we now have 3 of them because we've entered 3. And it's seeing them all. So let's put a couple more in. These are not Wikipedia. These don't have Wikipedia for their domain name. These are the websites of those 2 databases. And we'll put those in there. Okay. We're going to save one of them for nefarious purposes later on. Okay, and how many nodes do I have now? I have 5. So these are all going in there, and they're all different, so there's no issues with the thing. So here's one way I can get a hyperedge. I want to pull out all the things from that database that have the same, that have that Wikipedia domain name. So let's do that. And how many do I have? I have 3 of them, which is how many I put in. So a hyperedge is going to be given by a property or something like that. And I'll tell you more about what something like that is. It's a set of all things that have a common property. So if you want to if you want to have a bunch of nodes belong to a particular hyperedge, well, a property that each of those nodes has is that it belongs to the hyperedge. In this case, the hyperedge is specified by the domain name.
Is the thing that the get tufos gives you back, is that just a list, or is it like a special Synapse object? That you
It's a list of tuples which have a unique identifier and a dictionary that has all the properties you put in.
But so you can't call get tufos by prop again on it and then like continue to produce this?
Oh, you could do get tufo by prop, and it would give you just one.
Okay.
And then, I don't know if you did it again, if it would give you another one. But that would make sense. I just didn't think of that. And didn't check it. Okay, so in the process of working with a data, you may make a judgment about a particular node, and you can append that judgment to the node with a tag. So for example, for one of those Wikipedia links, the first one, whichever one that one was, I'm going to add a tag to it that says incomplete. Like I didn't think somebody did a good enough job of saying stuff about that web page. Yeah.
What's the difference between a tag and a property?
Tags are easier to get rid of. Tags are easier to add. You don't have to declare ahead of time.
Can you change properties after it's been created?
With some pain. So yeah, you want to think about what properties you want before you do it. Okay, so I'm going to, did I do these? No, not yet. So I'm going to declare these guys to have a tag that says incomplete. And it tells me, let's see. Oh, there's my tag. And that's the timestamp that tag was added. I can get rid of that tag later on if I don't think it's true anymore.
So tags are just tags. You can't give it like a specific value. It's just when you added the tag.
Yeah, well, no. You can do a lot with tags. You can have hierarchies of tags. And I've never really worked with tags all that much, so I'm not the right person to talk about it. Okay, so in fact, this is when I was writing this talk, was the first time I ever actually tried to use a tag. And it worked. So here I'm going to get all the incomplete tufos. I can get tufos by tag. And I got both of those guys. So hyperedges can be specified by a tag as well. So what I'd like to do now is I'd like to do a small little traversal of this small little graph. And from the nodes that have a tag of incomplete, I want to find all the tags that have the same domain name as the tags, as the nodes that were tagged incomplete. And so I have this wee little code to do that. Unexpected indent. Why do you not like my, oh, because I killed the colon. Let's try now. There we go. Okay, so one of those tags, one of those incomplete tags was on a Wikipedia page. So I pulled out all three Wikipedia web pages, and then there was the other, was it a DB? Yeah, it was the OrionDB web page that had an incomplete tag, and I only have one of those on my website. So instead of pulling out all 5 nodes, I pull out just the 4 that are connected to an incomplete node by having the same domain name. So here are some more things you might want to know about. If you want to get rid of nodes, you can do it with a delete tufos by property, which will allow you to delete a tufo by, for example, a primary property. Okay. Second of all, there's something that they call slices. I do not know why they call it slices, but it's used for bulk ingest and bulk manipulation of the node properties. Okay. So slices offer a efficient way for large-scale modify of the database. So for example, to delete nodes, you would do a core.slices, and then you would have a list of tuples. Okay, and the tuples would say which form was the node you wanted to delete, and what was the primary property of that form. And that's like 3 times as fast as trying to use a del tufo by prop. You can add tufo. So here's when I wanted to make my hypergraph database, I did not want one of their forms. Okay, so I added a new form, and I added some new properties using these functions, and they told me that I'm doing it in a really clunky way, and so yeah, I confess that I'm doing it in a really clunky way, and that's about all I have for you.